I hope my screen is visible to all. Yes, everyone, my screen is visible to all. So I think the week 7 start with gain bandwidth product. Okay, in the last Tuesday class, we already discussed that one. Now we are again go to the week 7 gate bandwidth product. Is it correct? Just tell me yes or no, basically, because I can't see your message again and again. Yes, who is asking the doubt in week 7? Mageshwaran. Yeah, week 7 start with the gain bundle, correct?
Yes, sir.
So till now, what you discussed that your gain A V naught is something A times V1 minus V2. Okay, where A is dependent on the either the inverting or non-inverting. Okay, if we are talking about the inverting, the A is minus RF by R1, and if we are taking the non-inverting, the A is 1 plus RF by R. Okay, so we write the equation V naught is equal to minus RF by R1, V1 minus V2. Okay, simply. So this V out is constant with respect to frequency. That is considered as a ideal gain. Okay. In this case, ideally gain if we are taking the op-amp is also ideal. So the value of A is we are taking the infinite. So V out is maximum. Okay, but practically A have some finite value. But again, this situation is the ideal situation. Why it is ideal situation? Because the output voltage is not a function of frequency, or we can say the amplitude gain, amplitude basically gain, operation amplifier gain is also not a function of frequency, and that is not possible. Anyone tell me why it is not possible? In place of writing, anyone why it is not possible? Because every component, if you increase the frequency, what will happening? The electrons and holes, basically vibration is increases. Vibration. Okay, and a simple example is the microwave oven. What is in that microwave oven? Because of providing the high frequency, there is a lots of vibration. If there are the lots of the vibration, so that means electron collision will be higher. And because of that electron collision, because when electron will collide with some other electrons, so they will release some energy. Okay, so if electron collision is higher, that means the energy will be higher. So that particularly will be creating a heat. Okay, and because of that heat, we can use that particularly heat to for the cooking purpose. Okay, so that is the concept of oven microwave oven. So basically the microwave frequency. So if we increase the frequency, there are the vibration is increased, electron hole vibration is increased, and because of that one, your response will be completely changed. Okay, your response is completely changed. You can't say that if your diode, like for example, I am taking the example of diode. If you are saying that your diode characteristics is like that, so that particularly diode characteristics is okay for a low frequencies. If your frequency is low, that frequency is fine, that particular graph is fine. But if you increase the frequency, you can't get this particularly diode characteristics. You have LT spice. Okay, you have LT spice. You can apply the signal LT spice. You simply take one diode, apply the frequency, increase the frequency value, and now you can check the what is the response. Okay, so every particularly component, electronics component where the electrons and holes are available. So you can't say the response of every component is not dependent on frequency. That is always a frequency dependent. Okay, that is always a frequency dependent. And if I assume that my gain A is a function of frequency in the operation amplifier, so that particularly operation amplifier op amp is the practical op amp. Okay, or we can say the non-ideal op amp. Okay, so this is the non-ideality in the op amp. Okay, now to define this particularly frequency effect of the op amp, we just consider that V naught upon V in, that is simply the difference between V1 minus V2 is A naught upon 1 plus S upon omega, where A naught is what? The DC gain. Okay. Till now, we are assuming that this A is simply DC gain, that is no frequency dependent. So that is called the DC gain. Now I represent this one is the A naught. Why? Because the complete this part will be considered as A. Okay. So for ideal op amp, the gain is A, but for the practical op amp, the gain is A naught upon 1 plus S upon omega. Okay, and this particularly A naught is the DC. Okay, now here if you see one particularly component of the omega will be arises. So if I say the V naught of j omega upon V in of j omega, that is V1 minus V2 is A naught upon 1 plus j omega upon omega. Okay, if omega is 0, so this component is 0, so V naught j omega upon V in j omega, that is simply A naught, and that is 1 plus R by R1 for the non-inverting, and minus RF by R1, not and, or minus RF by R1 for the case of. Understood? But if we increase the frequency, if we increase the frequency, the V naught of j omega upon V in of j omega, that is A naught upon, if I take the magnitude of this component, so that is 1 plus omega upon omega d whole square and root of this one. How we take the magnitude of complex quantity? Real component square plus imaginary component square and square root of this one.
Sir, what is omega d?
This omega d is, yeah, I just tell you what is the omega d. Okay, so omega d is basically the open loop. If I use the operation amplifier without connecting any circuit, so that is called the open loop. Okay, so the open loop bandwidth is called the omega d. Okay, that means if I use the operation amplifier without connecting any circuit, so that particular operation amplifier is dependent on some frequency component, or basically provide the bandwidth. That bandwidth is called the omega. Clear?
Clear, sir.
Okay, like for example, I am using this operation amplifier. So if I am taking the ideal operation amplifier, so what is happening is that this is my response. This is sometime my response. Okay, so this is the bandwidth omega. Okay, we call them the dominant pole frequencies also. Dominant pole frequency. What is the meaning of dominant pole frequency? If you understand the, I think you are aware about the Bode plot. Okay, I think you are aware about the Bode plot. So if you remember the numerator upon denominator, if any transfer function is given in the form of numerator upon denominator, so numerator will be give you the zeros and denominator will be give you the poles. Okay, so here if I represent a naught upon 1 plus j of omega by omega d. So what is the zeros frequency? Because no zeros are available, that is the only constant term. Okay, so that means zeros frequency is not available, but one pole is exist. And what is that pole location? How we calculate the pole location? Just omega upon omega d is equal to 1. Okay, so that means omega is equal to omega d is the location of pole. Location of pole. What happened at this pole? At this pole, you are getting slope change. How much slope you change? Minus 20 dB per decade. If you understand Bode plot, if you already remember Bode plot, so I think you are okay. So that is only for the recall purpose because you already discussed the Bode plot. If you are not too much aware, you will discuss that one in the control system also. Okay, so we are not going too much on the Bode plot part. So that's why where the pole will be exist, that is the omega d point. Okay, why it is called the dominant pole frequency? Because after that you are getting a slope. Okay, so that pole is the dominant pole. So it is also called the open loop bandwidth, or it is also called the dominant pole frequency. Fine? Any doubt? Okay, now what
No
happens
doubt, sir.
if omega is equal to omega d? If omega is equal to omega d, what happen? A naught upon 1 plus omega upon omega d square and root of this. So that is the a naught upon root 2. What is called this one?
3 dB bandwidth.
3 dB bandwidth. So at omega is equal to omega d, you are getting a 3 dB bandwidth. So that's why it is called either the open loop bandwidth or the dominant pole frequency. Okay, anything you can use. Now if we increase omega is greater than omega d, a naught upon root 1 plus omega upon omega d will square. So if omega is greater than omega d, that means omega upon omega d should be greater than 1. So can I neglect the 1? So it is a naught upon this. You can neglect this one. Now square and square root will be cancelled out. So this is the omega upon omega d remaining. So that is the a naught omega d upon omega. Okay. Now this is the magnitude response. So if I say the magnitude response is 1, so if I put the value of a naught omega d upon omega is equal to 1, so from that one I calculate omega is equal to a naught omega d. Okay, and at this frequency I can say my magnitude will be 1. So that means this particularly frequency is called the unity gain frequency, or omega, so we can write as a bandwidth also.
So for non-ideal op-amp, this is the unity gain, right?
Yeah. For the ideal op-amp, no effect of the bandwidth, because we are always consider the gain is constant. Okay, so unity gain bandwidth basically arises for the non-ideal op-amp condition. Okay. Yes. No. Any doubt?
Yes.
Okay.
Sir,
Now
can
you
you
get.
please elaborate on that 3dB bandwidth graphically?
Okay. Okay. I just tell you. Wait a minute. Now this a naught upon omega naught. A naught is what? It is a DC gain, and omega d is called open loop bandwidth, or we call the dominant pole frequency, DPF. I just directly write down the dominant pole frequency. Dominant pole frequency. Okay. So that means this particularly component a naught omega d is simply called the gain bandwidth product. Okay, because it is a gain, it is a bandwidth, and multiplication of this one is the called the gain bandwidth product. So gain bandwidth product is simply where your magnitude of transfer function is equal to 1. So how we calculate the gain bandwidth product? Simply calculate the magnitude of transfer function, equate that one is equal to 1, and after that you will calculate the gain bandwidth of omega. Okay, so for example, we are getting a transfer function is 2 upon 1 plus s by 100. Simply calculate the magnitude. This is the v naught upon vi, v in. Simply calculate the magnitude v naught upon v in magnitude. Okay, and after that equate is as equal to 1. Okay, so from here you calculate the omega, and that omega is simply gain bandwidth product GBP. Clear? Any doubt in this part?
How that omega became the gain bandwidth product? Like It's last step.
The value of omega, because it is a unity gain. We calculate this one with the unity gain, okay, and this particularly is called the gain value. Because omega is when we put the omega is equal to 1, sorry, omega when we put the omega is magnitude is equal to 1. When we put the magnitude response is equal to 1, we calculate the value of omega. Okay, and in the terms of omega, we are getting the a naught and omega d. What is a naught? It is a gain. And what is the omega d? It is a bandwidth. Okay.
Okay.
Omega is nothing but a multiplication of gain and bandwidth. That's why we call the gain bandwidth product only in the condition when we put the magnitude response is equal to 1. Fine. Any doubt?
No, sir.
Okay. Now we plot the Bode plot. Okay. Like for example, we have this response. Okay. This is called the omega. Okay. Not this one. This is my response. Okay. This is omega d. Okay. Any doubt? This is the log of a naught, and this is the sorry, this is the a naught in dB, and this one is the log of, because Bode plot will be plot between the log omega and magnitude in dB. Okay. Now, if I put magnitude response a naught is equal to 1, we calculate omega is a naught omega d. Okay, if we put a naught is equal to 1, we calculate omega is nothing but a naught gain v naught upon v in dB. This is the v naught upon v in. If I put v naught upon v in is equal to 1, I will get omega is equal to a naught omega. Now, if I calculate in the dB, convert this v naught upon v in dB, so v naught upon v in dB is equal to 0. Why? Because it is a 1. If I calculate the in dB 20 log of 1, that is 0, because log 1 is 0. Okay, so this is the graph, this is the 0 dB. This point is a naught. Okay, this particularly portion is called the gain bandwidth total. Okay, now if we reduce the gain, it will be increasing. If we reduce the gain, automatically this point will be increased. stupid. If you increase one more gain, mhm, just wait a minute. If you reduce more gain, this will increase. Okay. So if you reduce the A naught, you have to increase the omega d point. Here it is omega d this point. Now this is the omega d point. This is the omega d. So the multiplication of this component will be constant. Sorry, this point. Okay. Yes. Any doubt?
No, sir.
Fine. Now you are talking about the 3 dB. Why we call the 3 dB? 1 upon root 2. What is your question?
Yes, sir. That is my question.
Now if we are talking about the bandwidth, upon magnitude plot. Remember, first one is the Bode plot. Now we are plot the response. Okay, so this is my response. This one is the response. Okay, so basically, if I am talking about the low pass filter, what is the low pass filter? Says the signal that will be passed completely, that is the pass band, where we start the signal stop, it is called the stop band. Okay, so ideally if we are talking about the low pass filter, the response of the low pass filter is like, but we know the transition from the pass band to stop band on a single time period or single frequency, it is not possible. You already discussed in the signal system that if we are designing, if we are creating the impulse response, so ideally impulse response is straight line, but practically to generate an impulse response is it not possible. Okay, they have some particular transition, like for example, if we are talking about the impulse signal, so ideally impulse response is like that, but practically it will be having some width. Remember that one, or in the digital also you discuss transition. Okay, the similar concept is here. The transition from the pass band to stop band at a single frequency is not possible. So it will be start transition from here, it will be stop here. Okay. Now, what we consider as a pass band, what we consider as stop band. So we assume if the magnitude A is this one, so we are taking, this is the A upon root 2, is one frequency, okay, where the magnitude will be reduced 1 upon root 2 times of the original magnitude. That frequency is omega c, and this omega c is nothing but a band or cutoff frequency, and we call them as a 3 dB bandwidth. Why we call the 3 dB bandwidth? Because it will be reduce the magnitude by 3 dB. Okay, initially magnitude is A, now the magnitude is A upon root 2. So how much magnitude is reduced? 1 upon root 2 times. Okay, if we calculate the value of 1 upon root 2, so 20 log 10, 1 upon root 2. So that is a 20 log 10, sorry, log 1 minus 20 log root 2. Okay, I break in two components. This one is 0 minus, now if I calculate, so 20 log 2 power 1 by 2. So it is a minus 10 log 2. Log 2 is 0.3010 multiplied by the 10 with the minus sign. So it is a 3.01 dB or 3 dB with a negative. Okay, so if we reduce the magnitude 1 upon root 2 times, so simply in the dB it is a minus 3 dB. The magnitude will be minus 3 dB. Here if it is a, we say it is a 10 dB, so here it is automatically the 7 dB. Okay, and normally if we are talking about a normal magnitude, so if it is a 1, so it is a 1 upon 2. That's why it is called a 3 dB bandwidth. Okay, this is your question, I think. Why we call the 3 dB bandwidth?
Yes, sir.
Okay, now after that professor will be start with some questions, some examples. So they are taking not okay, either we are using the register or we are directly connected to that one with the negative. They are using the R feedback. They are saying, yeah, I think so. Okay, just check the value. This is the only resistance value. So other, I think they will use some other KI. Okay, so as we know already, we see that if we are talking about this resistors, so no current will be flowing. If we are talking about the ideal. Okay, if we are talking about the ideal of them, no current will be flowing. Why no current will be flowing? Because we consider that Vi is nothing but V1 minus V2, that is simply 0 because of a virtual ground concept. So the voltage at this point, no current will be going inside because both voltage potential will be same, 0. Okay, so if no current will be flowing, that means the drop across this resistance VR is also 0. If no drop across this resistance, so we are getting the Vi voltage here. Okay, now this is the Vi, so we are getting Vi here. Okay, if this is the Vi, what is the value of this one? What is the value of this one? So we solve that one. Vi is nothing but if I say the current will be flowing in this direction. Okay, so VAI is nothing but the drop across this resistor. So what is the drop across this resistor? Vi is equal to V naught times R upon KR plus R. Okay, the current flowing is the V naught upon KR plus R because no current going in this direction also. Okay, so the current flowing is V naught upon KR plus R, and the drop across this resistance, so multiply with the resistance. So we are getting V naught upon K plus 1. This is the simple concept, or we can say V naught is equal to k plus 1 times vi. We can simply written as a 1 upon r, 1 plus rf by ri time k. Okay, that is all about the ideal op amp. But in practical op amp, if we are talking about the practical op amp, we can't say the V1 is equal to V2 because in the case of practical op amp, no virtual current. Okay, no virtual current. So what we do, we have to calculate V1 voltage, we have to calculate V2 voltage, difference V1 minus V2 and multiply with the A, that A is also a function of frequency. Okay, function of frequency. Okay, and multiply this once. Now we get the V. This is the approach to solve a question in the case of non-ideal, or we can say the practical. Is it clear?
Yes, sir.
Now, if we consider that this is the V1, okay. So I am, for the simplification, I just assume that there is no particularly resistor. Okay. So that means if no resistor, so no voltage drop. So here we are getting the Vi. So my V1 is what? Vi. Now we have to calculate the V2. What is V2? V2 is the voltage at this point. Okay, voltage at this point. So how we calculate the voltage at this point? So the V0, the current will be flowing in this direction. Okay, so I can say the drop across this particular resistance is V2. So V0 divided by the KR plus R, that is the flowing current. If I multiply with this resistance, so this is the voltage. Okay, that is simply V0 upon K plus 1. Okay, this is the voltage at the second terminal V. Now we have to calculate V1 minus V2 and multiply with the A, we are getting a V0. Okay, so if V1 is Vi minus V2 is V0 upon K plus 1, okay, times A is equal to V0. So we have a two terms of A V0. So I just take a Vi is equal to V0 is already here. A V0 upon K plus 1 when I take to this right side. So it is a V0 times A upon K plus 1. Now take a common V0, so 1 plus A upon K plus 1 is equal to A times K. So V0, if I take a LCM K plus 1, it is a K plus 1 plus A is equal to A Vi, and V0 upon Vi is what? A K plus 1 upon K plus 1 plus K. Okay. If I divide with the A or divide with the K, so K is sorry constant. Okay, so we have to convert now A. Now the thing is that A is, I already discussed that it is an open loop gain. Okay, A. So A is sometime like, for example, I am taking it is 1000 by S because it is a frequency dependent, non-ideal op amp. practical op-amp, so that is dependent on the frequency. So A, if you see that it is 1000 by S. So what should I do? I just divide this equation completely with the A. So K plus 1 upon 1 plus K plus 1 time. Okay. Now this term is the constant. Why I divide with the A? How we can recognize that we divide with the A or we divide with the K plus 1? So we have to convert this particularly function, transfer function, in a form where the numerator is a constant term, because we call that numerator as a DC gain, as a DC gain. So K plus 1 is the constant term, A have the S term. Okay, A has the S term. So we have to eliminate A from the numerator. So that's why we call them this particular numerator as a DC gain. If there is a omega term available in the numerator, so we can't say that this is a DC gain. So we have to convert that one in a form where the numerator will be the DC gain and denominator will be providing me the bandwidth. Understood? So that's why I divide with the A. So it is a K plus 1 upon 1 plus K plus 1 upon A. Now you put the value of A and convert this to the transfer function. Any doubt? And now if I, in the example, if I am taking the A is 1000 by S, so I put the value. So K plus 1 upon 1 plus K plus 1000 multiply with S. Okay. I compare this one. So P naught we are getting V naught upon V in is we are getting K plus 1 upon 1 plus K plus 1 into 1000 divided by S. Okay. Now I compare this one with A naught upon 1 plus S upon omega. A naught is called DC gain. Omega D is called frequency or open loop bandwidth. Okay. And A naught multiplied by omega D is what? Unity gain bandwidth. Because if A naught is 1, so it is only omega D. So omega D is bandwidth. So that's why it is called the unity gain bandwidth. A naught omega D. Okay. Now if I compare this one, so I am getting the DC gain is K plus 1. I am getting omega D is, so I replace this one in the term K plus 1 upon 1 plus S time 1000 upon K plus 1. So omega D is what? 1000 upon K plus 1. Okay. And what is the A naught omega D? Unity gain bandwidth is K plus 1 times 1000 upon K plus 1. K plus 1 and K plus 1 cancel. That is the frequency is 1000. Okay. What we put? This one. Okay. What is the A is a 1000 by ds. So the gain is omega d by s. So we get the frequency bandwidth 1000. We get 1000. Okay. Now if we want a 3 dB bandwidth, what is the 3 dB bandwidth?
A
Then
upon
omega is equal to omega d. discuss here, no? What is the 3 dB bandwidth? When omega is equal to omega d, it is called the 3 dB bandwidth. So what is the 3 dB bandwidth? 1000 upon k plus. Okay. If, for example, I put the value of k is equal to 2. Okay, what is if for the case I get omega is equal to 2. So omega and omega, the 3 dB bandwidth is 1000 divided by 3. So 333.3 hertz. Okay, and what is the a naught omega d? That is the 1000. So if I plot the response, it will start decreasing from here. Okay, you can say it. Okay, so if I am talking about the polyplot, it will be start decreasing from here. So I'm talking about polyplot, the graph will be like. Okay. So this point is 333.3 hertz because this one is the omega d and this is 1000 hertz because this point is a naught omega. Okay. Any doubt?
No, sir.
So this is about the gain bandwidth. Now if we start with the next thing, I think the next topic is sine wave with 180 degree phase shift. So the next is sine wave with 180 degree phase shift. Now we require a two different sinusoidal signal wave that is having a 180 degree phase shift. What is the approaches we are having? Okay, so simply we are basically we required a minus sign. Okay, because if I am plotting, one is the sinusoidal signal sine omega t, second is the minus sine omega t, so both signal will be having a 180 degree. Now point is that why we require this 180 degree phase shift? Can anyone tell me why we require this 180 degree phase shift? Any idea? Yes, anyone?
180-degree phase shift is required in oscillator circuit, sir.
Hmm. Yes, one thing is that we require the in the oscillators. Second, if we go with the communication system, okay, when we design, when we generate a AM signal, FM signal, so here we required a 180 degree phase shift. because one signal is sinusoidal signal with one frequency component f1, second signal is the 180 phase shift. Okay. Now if we add these two signals, so here it is a positive, here it is a negative. So what is we are getting? This positive loop will be cancelled out with negative loop. So the magnitude is 0. Okay. Pi by 2 it is a 1. Here it is a pi by 2 it is 1. It is pi by 2 it is minus. Okay. Similarly, if we go with this signal and this signal, again this is the positive loop, this is the negative loop. So addition of both signals will be 0. So if we add, if by mistake these two signals will be added by due to the interference, so we are getting a null signal. We are getting a null signal. So for this purpose we are using the 180 equation. For more details we will discuss that one if we are going with the communication part. So we required particularly 180-degree phase shifter in that two scenarios. Okay. So what is the approach we are getting? One approach is that we provide the sinusoidal signal. Okay. And second, we pass this sinusoidal signal through the inverting amplifier. We are getting here we are getting the sine omega t, and here we are getting a minus sine omega. Okay. Any issue in that particular scenario?
No, sir.
So why the professor will be discussing this complete mechanism, basically this lecture on generating a 180 degree phase shift. If there is no particular issue, we can directly generate the 180 degree phase shift. Then what? Okay. The simple issue is that if we pass this signal directly, if I connect this signal directly, and if I pass through the inverting amplifier where the feedback loop is there, after that we are getting the signal. So there we are getting the phase delay. So the purpose to generate a 180-degree phase shift is completely collapse. Why? Because if we are getting the 180-degree phase shift, okay, so one signal we are getting this one, okay, and one signal we are getting with delay. Okay, so addition of both signal will be not a zero. Okay, so the reason to generate a 180-degree phase shift in the communication part is not a fulfilled. So what we do, we have to require that particular signal through the system. So we are not getting a too much delay. Almost signal will be reaching at the same time. So the cancel out the requirement of this 180 phase shift will be fulfilled. Okay. So now, what is the approaches if we use a inverting amplifier? Okay, if we pass one with the inverting amplifier, suppose if I use the non-inverting amplifier here. So the issue of phase delay will be lapse. Okay, the phase delay issue is resolved. But another issue is there. And what is that issue? If we pass through the inverting amplifier, we are getting V naught upon Vi is 1 over 1 plus S upon omega n, and for the non-inverting amplifier we are getting V naught upon Vi is 1 over 1 plus 2S upon omega. Any requirement to solve it? So if you want, I can solve it also. I think that is minus plus, so the inverting directly connect to the output V naught. Okay, so we are getting the V naught here. Okay, A is omega n by S. Okay, so we are getting V out is omega n by S A time Vi minus V naught. Okay, so V naught down. So V naught 1 plus omega n by S is equal to omega n by S time Vi, and V naught upon Vi is omega n upon S plus 1 plus omega n by S. If I divide, because the numerator will be dependent on S, so that will be create 1 0. To avoid this one, I just divide with the omega n by S, so it is a 1 upon 1 plus S by omega. Okay, so this is for the non-inverting. For the inverting, plus um, not stronger plus. Okay, so at this point we are getting the V naught by 2. Because both voltage will be same, so the distribution across this particularly is V naught by 2. The voltage drop across this one is V naught by 2, and the voltage drop across this one is the V naught by 2 if both resistance will be same. Okay, now again use the formula V naught is equal to omega n by S A time V1. So V1 is a Vi minus V naught by 2. Okay, if I solve this one, so V naught upon Vi is simply 1 upon 1 plus 2S by omega. Okay, now the second problem arises is that we avoid the problem of phase shifting, but the issue with the bandwidth. The bandwidth of this signal is omega n, where the bandwidth of this signal is omega n by 2. Okay, any doubt? So what should we do in that situation? We just initially create the inverting amplifier. So we have to increase the bandwidth. Okay, and that will also create some interest, some particularly phase shift. Also, because what is the phase shift of this one? What is the phase shift between these two? Yes, how we calculate the phase shift?
Tan inverse of imaginary part divided by real part.
Tan inverse of negative. So first problem with the, if we directly apply, so the phase shift is maybe higher or lesser than the 180. Okay, maybe it would be higher, maybe it would be lesser than 180. So it is not. So we apply the inverting and non-inverting concept. In the case of inverting and non-inverting, we are getting the other problem. Okay, so we are trying to resolve it by some changes. The changes we are doing is, so we apply some resistor here, we apply some resistor here. Sorry. Initially we directly apply. Initially we directly apply this one. What we are doing this thing. Oh, sorry. If we are talking about the inverting, we apply the VI here, the resistor, this one is the, and for the non-inverting, I this is the V0, so we are getting here. So this one is VI minus V0 time omega u by S, that is, we are doing mistake. So V0 upon Vi is 1 over 1 plus S upon omega. The bandwidth is omega. Okay, and in this case, okay, this is the Vi. This point is the R, the R. So we apply the KCL. Okay, we are assuming that this is the VA. So Vi minus Va by R is equal to Va minus V0 divided by R. Okay, so Vi by R plus V0 by R, that is Va by R, and we are taking this Va, so Va by R this side. So Va is Vi plus V naught times 2. Okay, and what is V out? V out is 0 minus Va multiplied by omega u by s. So V naught is minus 2 times Vi minus 2 times V naught divided by omega u by s. So V naught 1 plus 2 omega u by s is equal to minus 2 V by omega u by s. This implies V naught upon Vi is equal to minus 2 omega u by s upon 1 plus 2 omega u by s. So we have to remove this one. So it is a minus 2 upon 2 plus s upon omega u. If I take a 2 common, 2 omega u, and this 2 will be cancelled out. So 1 plus s upon. R. Sorry, this is, if I take it the 2 Va by R and R cancel out, so this is the Vi by minus Vi minus V divided by 2. V naught plus V naught by 2 omega u by s is equal to minus Vi by 2 omega u by s. If I take a common, so it is a V naught 1 plus 1 by 2 omega u by s is equal to minus omega u by 2s times Vi. So V naught upon Vi is minus omega u by 2s upon 1 plus 1 by 2 omega u by s. So if I take a omega u by 2s common, it is a minus 1 upon 1 plus 2s by omega u. So bandwidth is omega u by. Kindly correct this one. So what we have to do to combine both circuits. So one is the non-inverting minus this is the inverting. We connect a Vi. With the same Vi we are connecting here. Okay. In the previous circuit, if you see, we are connecting the negative terminal directly. Okay, so we are getting a bandwidth of omega. Now we apply upon R, like if we apply R here. Okay, if we apply R here, so we are getting minus Vi upon, sorry, here we are getting V naught upon Vi is equal to minus 1 upon 1 plus 2s upon omega. Okay, now for this one we can calculate. So this is the V naught. So here we are getting the V naught by 2. Here we apply the Vi. So V naught is equal to A that is the omega n by s time Vi minus V naught by 2. Okay, so if you see in the previous, this one, in the previous, we are getting the Vi minus V naught. Now we are getting the Vi minus V naught by 2. So if I solve this one, so V naught 1 plus 1 by 2 omega n by s is equal to omega n by s times Vi. Can you see this equation and this equation is almost same? V naught 1 plus 1 by 2 omega u by s is equal to, here it is a minus, in this equation it is a minus, here it is a plus because it is a non-inverting amplifier. Only the difference is this two. Only the difference is this two. So almost similar. Now if we calculate so V naught upon Vi, so we are getting omega n by s upon 1 plus 1 by 2 omega n by s. Okay, and if I take a omega n by 2s as a common, so it is a 2 upon 1 plus s 2s by omega, 2s by. Okay, so we convert this one. Now we are getting phase shift is 180 degree. Okay, both will be the same, but here it is a negative, it is a positive. Okay, the phase shift 180 degree will achieve. Second, bandwidth. The bandwidth is omega n by 2. Here we are achieving the bandwidth omega n by 2. Here we are achieving the bandwidth omega n by 2. This is achieved. Third, amplitude. Okay, we doesn't achieve that. Why? Because here the amplitude is 1, here the amplitude is. So what should we do? If we apply the input voltage Vi by 2, apply the input voltage Vi by 2. So we are getting Vi by 2, Vi by 2. Now you can check this equation and this equation, both are same. Only the difference is minus 180 negative sign. Okay, so that means we achieve the phase, we achieve the bandwidth, we achieve the amplitude. Any doubt? So both equations will be same. That means we are achieving everything: the phase, the bandwidth, the amplitude. Now, how can we do the Vi by 2? How can we apply the Vi by 2? That means we have to apply the input voltage and with the help of
Resistive divider.
resistive divider. Okay, so we are using VA, we apply this particularly R, apply this R, and apply this to ground. Okay, so here we are getting the voltage VI by 2. So this problem is also resolved. Okay. Any doubt?
No, sir.
So this is the way to create a 180-degree phase. Now after that, what is the topic we are taking? After that, anyone tell me what is the next topic?
Input offset current compensation.
Okay. Okay, I think Professor, after that we will discuss one more thing is that in place of this circuit, what should we do? We are getting Vi from here. Okay. We apply R here. Okay. Because this is the point Vi, this is the point, okay, and these two resistors. Okay, and this one is connected in place of this one. This one is connected. Okay, so they will break this one into the one another circuit is we directly connect here. This. This. Now the next topic is input offset current. So, so what is the meaning of input offset current? Yes. What is the meaning of input offset current? About this is my operation amplifier. Okay, this is the V1, this is the V2. This particular voltage source having the voltage is A times V1 minus V2. So we are getting this particular resistance. Okay. So here we are getting output, that is the A times V1 minus V2 minus, if I say the current I is flowing from that one, so I multiply by the R. Okay, this is the R out and this is the R. Okay, is it clear? We already discussed this thing in the starting. Okay, this is the internal diagram of operation amplifier. Now, if I say my R out is very less, that's why I assume that in the case of ideal op amp, the output impedance resistance is 0, but practically it is not possible, so we are taking a minimum resistance. So that means the drop across this one will be the minimum. Okay, so my output voltage is A times V1 minus V2 minus IR out, and that will be the negligible because R out is small. Okay, now if I say my V1 is equal to V2 that we consider in the ideal op amp, so I assume that no current will be going inside, every current will be passed through the feedback circuit. That we consider in the case of ideal op amp. But practically, if I assume that if V1 is equal to V2, that means V1 minus V2 is 0. If V1 minus V2 is 0, so V out is A times 0, that is also 0. So we are not getting the output voltage. Okay, we are not getting the output voltage. So in that situation, what we assume that V1 is approximately V2, but not equal to V2. So we are getting V1 minus V2 is not equal to 0. It is approximately 0 but not equal to 0. Okay, approximately it is 0 but not equal to 0. Clear? Any doubt? And if it is not equal to 0, that means the potential at this point and the potential at this point is not possible to 0, not equal. If the potential is not equal, that means the current will be flowing. So if I say this is the Ix, okay, and this is the Ix current, so I say that if V1 is not equal to V2, the current Ix is V1 minus V2 divided by Rn. Okay? Ideally, we assume Rn is infinity. Okay, but practically we assume the Rn is maximum in terms of mega ohm. Why? Because if Rn is the maximum, so the voltage difference between these two will be maximally drop across this thing. Okay, so Rn is maximum. If Rn is maximum, so I can say Ix is minimum, but never be a zero in the case of practical op amp. Okay, ideally Ix is 0, but practically Ix is minimum, very small, but never equal to the 0. So what we assume, we are saying there are some current is in this particularly op amp going inside. So we are saying that it is the Ix current going inside. This is also the Ix current going inside. Okay, and if current will be flowing, So we assume there is one battery will be there, or in the third week we already discussed that if we use a capacitor with the infinite value, so that will also behave as a battery. So we are connecting one battery that will be used as a, we are using the infinite capacitor that will be used as a battery to provide this IX current. Okay, any doubt in this?
No, sir.
Yeah. Now, if we apply the operation amplifier in a in non-inverting mode, non-inverting amplifier, so we apply one signal, Vi, along with that we connect with the R. Okay. Now we have some battery that we are using the positive terminal, negative terminal we are connecting resistor. Okay, and I am saying some current will be going inside this one, so this is the IX and this is the IX current. Okay, now the thing is that if we connect a capacitor, if we connect a capacitor, so the capacitor blocks the DC signal. Okay, so the question is that what is the output? Yes, what is the output? Anyone?
It is 0, sir.
It is zero. Why?
For DC, the capacitor acts like an open circuit, so Vn equal to 0.
Okay, Vn is equal to zero. Okay, if Vn is equal to zero, so V out is simply if I am taking 1 plus Ra by R1 times Vn, so that is zero. Okay, so for the ideal case, we consider that this is the zero. But what about the in the practical case? We can't identify. So V naught we can't identify. because if current will be flowing inside that one, I am saying that current will be Ix will be going inside the operation amplifier. So that means the voltage applied input of the operation amplifier is not zero. Okay. So my V out is A times V1 minus V2. That is not zero because Ix will be flowing. The value of Ix is minimum, so that means the value of V1 and V2 should be minimum, but it never be zero. Okay, so without applying the input, some current will be flowing inside the op amp. Okay, without applying the input, some current will be flowing inside the op amp, and that particularly is called the input offset current. That is called the input offset. Okay, now that particular input offset current introduce some error. That is called the offset. Okay, so in that scenario, what we have to compensate the input offset current okay. So when we are applying the V is equal to 0, my output voltage is also 0. That is called the input offset current compensation. I think so. What we have to do in that scenario, we have to apply some particular voltage here. Okay. I just said a Vref voltage. Okay, I apply some voltage here to if reduce the effect of the applied input current. Okay, the fluctuation in the input voltage To overcome this one, I add this voltage because this is connecting on the inverting terminal. Here the voltage will be applied on the non-inverting terminal. So if we are getting the VI 1 plus R by RF by RA minus if I use the VRF RF by RA. Okay, so basically because of this applied voltage, this effect will be created in the case of ideal op amp. So the output voltage we are getting a less. So initially if we are having a problem is V naught is equal to VI 1 plus RF by RI. Now this is the output voltage. Now we reduce the output voltage by adding the reference signal RF by R. So we compensate the error, compensate the output error. Okay, by applying this reference voltage. That is called the compensation. Now what is the value we apply on the reference voltage? So we will get, we are taking the ideal case, okay? So for better understanding. So if my VI voltage is this multiply by RI by RF, okay? If I introduce should be 0. So what is my VREF? VREF is VI into RI upon RF into 1 upon 1 plus RF by RF. Okay. So if we apply, we put the value of VI RI upon RF into 1 plus RF by RI. If we apply the reference signal voltage in this one, so both will be the voltage, output voltage will be 0. So we can say my complete circuit will be compensated. The output error will be compensated. Okay. Now if we take in the practical scenario, practical op amp or non-ideal op amp. So I have this one, this is a plus, VI minus directly connected to the Vout. This one is R. Here. Okay. So this point is VI. This point is V naught into R divided by R plus KR. So that is simply V naught upon 1 plus 2. Okay. So we have to compensate VI minus V naught upon K plus 1. This should be 0. Okay. So VI is equal to V naught upon K plus 1. Okay, so this point voltage is this one, V naught upon K plus 1. So what should I do? I have to add some voltage source here. No. We are taking that the VREF. So this point voltage is what? V naught into R upon K plus 1 times R because of this voltage, and because of this voltage we are getting a VREF. Okay, so overall voltage at this point will be the this one, or we can take it as a V naught minus VREF divided by R plus KR, that is the total current flowing, multiply by a drop across this resistance is R plus VREF. This is the voltage drop across this one. Okay, any doubt in this particularly statement how we write? So it is V naught. If I take a R common, so it is a 1 plus K minus V ref upon 1 plus K plus V ref. If I take a V naught 1 plus K plus V ref 1 minus 1 plus K. So if I am taking the LCM, so V naught 1 plus K plus V ref K upon 1 plus K. Okay, now Vi, that is the input voltage V1 minus this point voltage. This point voltage is this one. V naught 1 plus K plus V ref into K upon 1 plus K. Both voltage difference should be 0 to compensate the offset condition. Okay, if both voltage will be same, that means no current will be flowing. Current only flowing when the voltage difference, there is some voltage difference. So if I put that if both voltage will be same, that means the difference between them is 0. So we are keeping this. Now can I calculate the VREF voltage? So Vi minus V naught upon 1 plus K is equal to Vref into K upon 1 plus K. Okay, this is the minus sign. I take this one to this side. Now Vref is equal to Vi into 1 plus K divided by K minus V naught times K. Okay, so this is the value of Vref. Okay, similarly, if you are calculating the ideal, inverting op amp, where your equation will be, your graph will be like that. You are applying the Vi, the resistance value, negative. Here we are getting the one more resistance. Okay, positive connected with, initially it is connected with ground. This is the V out. Now after that, what we do? We add a reference voltage. Vref. Can you calculate the value of Vref? Okay, so this is the condition to reduce the to compensate the input offset current. I think that is clear to all. What is the input offset current compensation?
Clear, sir.
Yes, sir. Yes, sir.
Now, which one is the next lecture?
Op amp transfer function.
Okay. Current transfer function I think we already covered. So, we know the DI A naught upon 20 plus as upon omega. I think this is why we use this. Can I get to the slide? So that we know this is positive terminal, negative terminal. The A given by people. So the R out and the R. Okay. Now, if we calculate if we basically use the two-port network and solve it, so we are getting the V1, V2. This particularly internal circuit of this one. This this is the current source that GM1 this is the R, this one is the C. Here we are getting the V1, this is the A. Okay, so this is the transconductance sequence of transconductance equivalent. Okay, where GM1 is basically the transconductance. Okay, if I say the current will be flowing here is I1, so one current source will be there. Okay, if I say the current will be flowing I1, that is equal to A times V1 minus V2 upon R. Now A is I1 times R out, A times V1, A times V1 minus V2 is basically I1 R out, that is because IR basically represents the voltage, and that particularly will be the gain multiplied by the voltage difference. Okay, if I calculate the I1, so that is A upon R out into V1 minus. Now A is what will be the possible. If I say that AM is R times V, A is Ri times V. Suppose for an example, so I can say my I1 is R times I upon V into V1 minus V2 upon R out. So this is the resistance, voltage and voltage. So I will be there. Okay, and this I times V is basically called the G. So we convert my transfer function in the form of current transconductance form, where we are getting the value, we are getting the current. The current I out current is nothing but Gm times V1 minus. Okay, so here we are getting the Gm times V1 minus V2 in the form of current. Okay, so in this way we are getting this particular value Gm1 times V1 minus. Okay, now can you solve this one? So if I say the V out is what? A times V1. Simple. This- Okay, I am just saying the VI. VI is here. Plus and minus. Okay, so A times VI. And what is VI? This is the input voltage, that is the difference between V1 minus V2. Now, if I am talking about this is my VI, so can I write this VI in terms of capacitance, in terms of resistance, and in terms of this current? So if current is flowing, that is the Gm1 times V1 minus V2, that will be drop across this resistance and that will be drop across this capacitor. Okay, and that drop is nothing but the Vi. So Vi is what? Vi is if the current Gm1 V1 minus V2 will be flowing and drop across C1S 1 over C1S upon total resistance R1 plus 1 by C1S. That is simply the VI.
Sir, R1 and C1 is parallel, na?
Yeah. Hmm. So I can break that one is, this is the current source. Okay, can I convert into the voltage source? So it's R1, this is GM1 V1 minus V2 upon R1, that is C C1 or C, what we are taking, C or C1. Now what is the voltage drop across this point? It is clear?
Sir, GM 1 into V1 minus V2 into R1, sir.
Yeah. Here R1. Okay. So we are getting Vi, that is equal to, if I take a 1 by Cs as a common, so Gm1 times R1 upon 1 plus R1 C1s into V1 minus V2. This is the Vi. And what is V0? V0 is A time Vi, so I just multiply Gm1 into R1 divided by 1 plus R1 C1s times A to V1 minus V2. Okay, and V0 V1 minus V2 is simply A time Gm R1 upon 1 plus R1 C1s. Okay, so A time if I divide with the Gm R1, no, yeah, I can keep it as A time Gm R1 upon 1 plus S time 1 over R. This A time Gm time R1 is A naught, and 1 over R1 C1 is omega n. So that equation is A naught upon 1 plus S by omega. That is the V number form. Okay, so from here the transfer function will be done. Okay, this is the constant term DC, and this one is, we know that 1 upon RC is the frequency, so 1 upon R1 C1 is the frequency. So that is represented by the omega. Okay, any doubt? So how we get the transfer function in this form, A naught upon 1 plus y square? If we have a multiple op amp, one op amp along with the another op amp, plus plus the VI would be now. So what we are getting in the output, if this is the unity gain feedback, okay, so we are getting a VI here. Now again, it is a unity gain feedback, so this is the VI. Okay, if we have a feedback of 2, that is the 2R and R. So what we are getting is a 2VI here. Again, we are using R and 2R. So we are getting a, now input is 2VI, the input, and again is the 2. So we are getting a 4VI. So that means if we connected multiple operation amplifier in the cascade form, we are getting a multiplication. So if one transfer function is 1 plus s upon omega n1, second will be having the transfer function a1 plus 1 upon s by omega n2. If we have a third operation amplifier, then it is a a2 divided by 1 plus s upon omega n, and so on. Okay, and so on. How many operation amplifier we connected in the cascade form? According to this one, we are getting a transfer function in the multiplication. Okay. Any doubt in this one?
No, sir.
Now after that, I have a single stage amplifier stability, I think so. Yes, the next lecture is single stage. Single stage
It's a
amplifier.
single stage.
Yeah,
It's a single stage.
a
An
single stage
amplifier.
amplifier stability.
Yes, sir.
So basically, stability is dependent on what? In the Laplace transform, I think if you remember, we already discussed that one in the the previous Tuesday class. If you go with the Laplace transformation, so the Laplace transformation, how we define the stability of the Laplace transformation? If I have a 1 over s plus 2, how we check the system is stable or not?
The poles are in the left half pole.
Poles are in the left half pole. Nice. But only this thing is sufficient to define the stability? Absolutely not. Not define the system state. The only condition is defined that my ROC of Laplace transform S should contain j omega axis. Okay, if I have a pole in this direction and my signal is the right-sided signal, then it is stable. If it is a left-sided signal, that is unstable. So it is unstable, and if the ROC is this direction, then it is stable. I think discuss the ROC in the Laplace transformation. Yes or no? Yes.
Yes, sir.
Okay. So without ROC, we can't say the system is stable. But we know that this left-sided signal only we discuss in the signal system, because u of minus t, there is no existence of this signal in the electronics. How can you say that? Simply like, for example, I have a one supply, okay, I connected one switch, and here it is a bulb. Without switch on, the bulb is not glowing. Okay, without the switch on, the bulb is not glowing. So when the we switch on, or basically push the button, we consider t is equal to 0, and after that it will be start working. If I am considering t is equal to -1, the switch is open, no issue, because there is no existence in the electronics part. That means there is no circuit will be working in this t minus 1. So why we consider the t minus 1? That's why we are not considering the left hand signal, we are only considering the right side signal. So only for the electronics part, if we say if my pole will be in the left side, so I can say the system is stable. Only for the electronics, not for the signal system. Signal system without ROC, I can't say the system is stable or not. Understood? So we are not discussing the left side signal, we only consider the right side signal. And according to this one, we can say if pole will be lie in the left hand side, so I can say my system is stable. Now, if my pole will be moving toward the j omega axis, what happen? Stability reduces. So how far this particularly pole will be the exist? According to this one, we can define the system stable. Okay, only this parameter will be defined the system. So first of all, we have to calculate. We are giving the V naught upon Vi, that is A naught upon 1 plus S upon omega. Okay, so first of all, we calculate the loop gain. This is the simply A. A naught upon Vi is simply A. So we have to calculate the loop gain. So what is the loop gain? A beta. This is my system. A this is beta. So V naught Vi. Okay, so to calculate the loop gain, this is my loop gain. Okay, so this is my loop gain A beta. A is this one, so I just multiply A naught beta upon 1 plus S upon. Okay, now my transfer function is V naught upon Vi is A naught upon S upon. I multiply with beta and divide with beta. This A naught beta is my loop gain. So that is 1 upon beta loop gain upon 1 plus S upon omega. If I divide with the loop gain, let's say 1 upon beta multiply 1 upon 1 plus sorry, 1 plus S by omega n upon is 1 by beta 1 upon 1 plus loop gain plus S upon omega n. Okay, so what is the position of pole? Yes, what is the pole location? So 1 upon 2 equal to minus S upon omega n loop. So loop gain and loop gain cancel out, so S is equal to minus 1. Okay, so I can say this one is minus omega n. Okay, and the value of omega n will be decided that the system is the stable or not. Okay, so this is the open loop system. Okay, this is the open loop system. So we can say that open loop system is stable because we know that omega n 0 is not possible. Okay, the omega n value, because it is a frequency, so it should be greater than, or sometime it is equal to 0. So maybe possible that omega n will be exist in the left hand side or this particular equation, but towards the right hand side it is not possible. So I can say my open loop will be the stable. Now we go with the closed loop system. So what is the closed loop gain? That is a naught upon 1 plus, sorry, a upon 1 plus a. Okay, I multiply with the beta and divide with the beta. This is my closed loop. So it is a 1 over beta, a beta upon 1 plus. This a beta is the, so I just say that 1 upon beta into loop gain upon 1 plus. Okay, now if I divide, so 1 upon beta. If I divide, so it is a 1 plus 1 upon. Okay, what is overall loop gain? A beta is a naught beta upon 1 plus S upon omega for the known ideal of that. For the known ideal of that. So can I put a loop gain value? This one. So 1 upon beta, 1 upon 1 plus 1 over loop gain. A naught beta 1 plus S upon. That is a 1 over beta. If I take the LCM, so A naught beta is the LCM. So it is a 1 plus a naught beta plus S upon omega. Okay. Now the pole, where the pole will be exist. So what should I do? This 1 plus a naught beta is the constant term because a naught is a DC gain and beta is a feedback factor. Both will be the constant term. So S upon omega n is equal to minus 1 plus a naught beta, and S is equal to minus 1 plus a naught beta times omega. Okay. Now what is the stability factor in that scenario? So if a naught beta is greater than 1, so I can say that minus a naught beta times omega. Now a naught beta will be decided, the pole will be in the left hand side or the right hand side. Okay, this particularly a naught beta will decide it, my pole will be in the left hand side or the right hand side. If for example my feedback factor beta, that is negative, so S is positive, we can say the system is unstable. Can we verify this one, the system is unstable or not? So if you remember, in the first week we discussed, this is my A, this is my negative, and here I am using the beta, that is also negative. So what is the transfer function? So V naught upon Vi is A upon 1 minus A beta. We know that if A beta is equal to 1, V naught upon Vi is infinite, that means it is unstable. So if beta we take the negative, already the feedback system is negative. Again, if we take beta as the negative, we can say the system is unstable. Here we also see the system is unstable. Okay, and if beta is positive, this is the A1 upon A beta, it is always less not equal to the infinite, so we can say the system is stable. Here if I take beta as a positive, okay, so S is always negative, we can say the system is stable. Okay, so we check from here also, we check from here also. Okay, the max least possibility is that the A naught beta is 0. Okay, the least possibility is that A naught beta is 0. And if A naught beta is 0, what happens? The pole will be shifted towards the origin, shifted at origin. So maybe in that scenario, the system is marginally stable. Okay, if A naught beta is equal to 0, we can say the system is marginally stable or unconditionally stable. Okay, otherwise, in every scenario, it is stable. Otherwise, okay, and if A naught and beta is 0, that means there is no feedback. If A naught beta is equal to 0, that means either A naught is 0, this is 0, or the beta feedback is 0. Either A naught is 0 or beta is 0. Then A naught beta is 0 possible. And that is not possible if my system will be the feedback system. So that means it is always unconditionally stable. No condition will be there in which my system will be the unstable. Okay, fine. Any doubt you can ask. If no doubt, we can stop. Okay.
Clear, sir.
I think two stage is remaining. Okay, so we will take one class in that week. Thank you.
Thank you, sir.
Thank you, sir.
Now I think it is clear little bit.
Now